Hello and welcome to this Smart Eye webinar. First and foremost, I'd like to thank all of our attendees for joining the webinar today. There will be 3 Smart Eye members speaking during this presentation, and all 3 members work for the Research Instruments Division of Smart Eye. There's myself. My name is Aaron Galbraith. I'm the sales engineer for all regions of North America. And joining me today are Mr. Rob Wesley, North American Sales Director for the Northern region, and Mr. Brant Hayes, North American Sales Director for the Southern region. We hope you'll find this webinar useful in guiding you on what to look for when selecting an eye tracker. Questions may be asked at any time during the presentation via the Q&A section, and all questions will be queued until the end of the presentation. And then we'll take some time to answer a few of the questions live for you. So if you have any questions, please use the Q&A section. Please stick around and enjoy our presentation. So let's discuss the purpose of this webinar. First, we will attempt to assist you in making an informed decision when selecting an eye tracking solution. So there are a number of different eye trackers on the market with varying features and capabilities, and we'd like to cover some of the important characteristics that should be taken into account when considering what eye tracker to choose. After that, we'll highlight the features and capabilities of a 3D remote multi-camera eye tracking solution. But before we dive into the features of optical eye trackers, let's first give a small introduction to optical eye tracking. I'd first like to define what optical eye tracking is and then discuss the advantages that it offers to researchers. The definition or concept of optical eye tracking is that light is reflected off the back of the eye. The reflected light exits the eye and is then measured using remote cameras or another optical sensor. Mathematical calculations are performed to determine where the eye was looking. And there are some advantages to this, 4 major advantages. First, rather than simple observation of where someone is looking, which is rather subjective in nature, an optical eye tracker supplies objective data, which offers intuitive insight into human-to-human and or human-to-machine interaction. Second, by paying attention to where a subject fixates, as well as their gaze patterns, we can draw comparisons between the direction of the head and eyes for the purpose of understanding where the subject is directing their attention. And this may possibly offer insight into their cognition as well. Third, there's an old phrase that says, the eyes never lie. By tracking where a subject is looking, researchers can gain an understanding of how people perceive and interact with their environment. And lastly, by analyzing gaze patterns, researchers can gain a deeper sense in the processes of attention, learning, and memory. So let's cover some common basic terminology that's used in the eye tracking industry. First, the gaze. It's pretty straightforward. It's just a steady, intent look. A fixation. This is a gaze that's held for a period of time and typically within a bounded area. We have saccades, and these are rapid, jerky movements of the eyes. And these are common when the eyes do not have a moving object to track. We have smooth pursuit, and this is the smooth movement of the eyes. And this is typically occurring when there is a moving object that can be tracked. Note that saccades and smooth pursuit eye movements are mutually exclusive, but they do work in synergy for visual tracking. And we have perceptual span of the eye. This is used less often, but comes up occasionally. And it's the angular coverage area where eyes can perform accurate actions, such as reading, facial recognition, for example. For visualization, there are 3 concepts that are often associated with visualization. Rather than discuss them here, let's explore them using images. We have gaze trails and fixations. So the left image shows fixations as bubbles and gaze trails as the line between those bubbles. Gaze trails are often a combination of saccades and smooth pursuit actions by the eye as the eye moves between fixation points. Fixation points are typically visualized using bubbles or a numerical index, some way of tracking where the user's been looking. We have a heat map. This is often used to indicate gaze patterns across multiple subjects. Often researchers, this offers researchers the ability to quickly see what areas are frequently being looked at. In this image of Times Square, we can clearly see there's a large interest from people in the ads for Coca-Cola and Phantom of the Opera. And third, we have areas of interest, sometimes called AOIs. Areas of interest are sometimes called regions of interest as well, or ROIs, depending on who you speak with. Many tools allow AOIs to be defined and then offer metrics surrounding these AOIs. And they can be static AOIs, which means they're stationary objects, or dynamic AOIs, which means something that's moving and needs to be tracked. Metrics offered by tools may include how many subjects looked at the area, did they revisit the area, how long did they spend looking at the area, and how long did it take them from the beginning of the test to look at the area. So with that short introduction out of the way, let's examine 4 common types of optical eye trackers. So there are 4 main types of optical eye trackers. Note that each type has its own benefits and drawbacks, as well as suitability for various applications. First, we have glasses and head-mounted trackers. These are useful in many environments, but shine when mobility is a desired feature. They do present challenges for anyone who requires glasses to see or who have issues wearing anything on or around their head. An example of this technology use would be a supermarket shelving study for marketing research. Second, we have bar and screen-based trackers. These are useful in single screen applications where the cameras can be found mounted close to the subject. An example of this technology would be understanding where a subject's looking on a computer monitor. Third, we have remote stationary tracker. This is generally used for medical grade level research. Subjects are typically positioned very close to the camera, much closer than with a bar or screen tracker, and have very limited movement. This may be an issue for subjects who can't sit still for very long. However, the subject's limited mobility allows these trackers to operate at higher sample rates. An example here would be they can be used for early detection of Alzheimer's disease or for exploration of the relationship between glaucoma and eye movements. And fourth, we have 3D remote multi-camera solution. Subjects are positioned the furthest away from the cameras, relatively speaking. Cameras can be freely placed in the test environment. These type of trackers offer the largest headbox and field of view for subjects, which allows allowing subjects more freedom of movement and allowing researchers to track subjects' eye movements over a larger area. An example here would be tracking a pilot in an aircraft simulator to determine if processes or procedures are being followed correctly. So far, we've covered a high-level overview of optical eye tracking, some common definitions and types of optical eye trackers. I'll now hand the presentation to Mr. Rob Wesley, who will explain how to identify what requirements or features are important to you when selecting an optical eye tracker.
Thanks, Aaron. Purchasing the right eye tracking system for your research can be a very challenging process. As Aaron showed, there are many different types of eye trackers out there, and they all work well in specific applications and can have a wide range of features and capabilities. So before you decide on an eye tracking solution, you should ask yourself a few simple questions. What environment will we be testing in? What type of measurement parameters or metrics are needed? How would you like to visualize and analyze the data? And what advanced features and capabilities will be needed for your specific project? So we'll dive into these questions in a little more detail to help explain the importance of each. When looking at the environment, it is important to first determine where will you be testing. Will you be testing on a single display screen, or is the environment going to be a little more complex, like a multi-screen application, a simulator, a vehicle or aircraft cockpit, or an open space? Will you need the flexibility and versatility to use your system in multiple environments? Will you need scalability for future projects that will require a wider field of view? You should also consider what lighting conditions you'll be testing in, as sunlight and poor lighting can present challenges for some trackers. It is important to also consider the mobility of the test subject. Are they going to be stationary or seated, or moving around the environment freely? Will your test subjects be wearing sunglasses or prescription glasses? Or are your test subjects even willing or able to wear eye tracking glasses, which can sometimes be a challenge for younger or older participants. These are just a few of the environmental aspects you should consider. When looking at measurement parameters, it is important to consider what data is relevant to your research objectives. Nearly all eye tracking systems will provide eye gaze vectors. Some eye trackers leave it up to the researcher to calculate where the gaze is intersecting the environment. However, a few systems can provide not only gaze vectors, but also gaze intersections with real-world objects. This can be extremely advantageous, as you will see later in the presentation. If your research involves assessing drowsiness or workload, you will want a tracking system that can not only provide eye gaze data, but can also provide critical measurements such as eye opening data, including blinks, head position and rotations, as well as pupillometry. Another key question to ask is what level of accuracy is needed for your projects. Accuracy levels can range significantly depending on the system you choose. Sometimes an estimated gaze with lower accuracy is acceptable, which can often save cost. But there are many other factors that should also be considered. For instance, if you are interested in saccades or microsaccades, you should consider a system that offers a higher sampling rate. Sampling rates can range from 30 Hertz to over 1,000 Hertz. Many of our research clients prefer to use the raw data feeds without visualizations of the data. However, some researchers prefer to have additional visualization and analysis capabilities. Aaron presented some of the common visualization capabilities, such as gaze trails, fixations, heat maps, and areas of interest. But you can also utilize other features, such as data recording, logging, and playback, as well as graphical representations of the data, as well as pre-formatted analysis reports. Another important feature is performing gaze overlays. This is essentially laying the gaze over the top of a video or display image. One overlay method is used by taking a scene camera where the gaze is overlaid directly onto an image from the scene camera. This method works well. However, it will introduce parallax errors caused by the offset of the angle between the subject's eyes and the camera position. Another option is performing screen grabbing overlay, which is where the live video output from a display is split and laid directly into the 3D world model for finite gaze overlay. This method provides more precision and eliminates issues with parallax errors. Another capability of the visualization tools is merging multiple eye tracking systems together for performing simultaneous multi-person studies. In this case, you can see where the test subjects are looking at their screen and when they're interacting directly with each other. This capability can be used for worker-coworker evaluations, as you see here, or it can also be used for pilot-co-pilot studies. Research-grade eye tracking systems require capabilities well beyond your standard off-the-shelf eye trackers. We will explore some of these advanced features and capabilities that can greatly enhance and simplify your research. As mentioned earlier, almost all eye trackers will provide eye gaze vectors, but many standard systems will leave it up to the researcher to determine where the gaze vector intersects the test environment. This can require tremendous time and hassle recalculating the gaze intersections every time the subject's head moves. To avoid that, some of the premium systems can utilize a 3D world model to replicate key items in the test environment. The 3D world model is essentially a wireframe replication of important items in the test environment. This model allows the researcher to capture data in an XYZ format and to also see real-time gaze intersections with the critical items in the test environment without having to perform constant recalculations every time the test subject's head moves. As you can imagine, this capability greatly simplifies the testing and analysis process. Research-grade systems also tend to provide several data streaming options, such as UDP or TCP, to stream your data to another PC or simulator. They also support multiple file formats, such as Excel or MATLAB, or if you're doing automotive testing, They can even output to a CAN bus. Some tracking systems can even support integrating data feeds with simulators, test PCs, and other biosensors. This can even include timestamping and time syncing multiple data streams together using network time protocol. This timestamping capability is especially useful for analyzing reactions to stimuli during research. Some advanced systems can even include an API for remote control of the eye tracking system to start-stop data recording sessions and to perform a number of other tasks such as calibrating and user profiling. And finally, being able to record audio and video can be a critical feature for many research projects. As we've shown, there are many important features and capabilities that you should consider before purchasing an eye tracking system for your research projects. To help you, we put this brief checklist together that you can use it as a guide to make sure your system will have the capabilities that you will need for your upcoming projects. I hope you find it useful. So with that, I'd like to hand the presentation over to my colleague, Brant Hayes, who will provide a demonstration of some of these important features using SmartEye's 3D remote multi-camera system.
Thank you, Rob. So we've seen and discussed a few different types of eye trackers now. For this last part, I'd like to provide some visualization of some of the key components discussed by Rob in the previous slides that you'll experience with an advanced premium eye tracker. We're going to view a couple of different cases, which use SmartEye Pro, which is a multi-camera remote 3D head and eye tracking system. The first case that we're going to view is this control room environment that you see here. The requirements were to get precise tracking within 1 degree of accuracy on the left monitor, the control panel underneath, and the radio control display at the bottom. They also wanted to capture gazes or looks at the right monitor as well, but no accuracy was required. The scalability and the flexibility of the multi-camera system allows us to accommodate these requirements from a remote perspective and really get naturalistic behavior with the subject throughout the experiment. So to meet these requirements, we put forth a 5-camera configuration, which you see the cameras in red, with 3 IR flashes, which you see in yellow, which we'll discuss a little bit later. So now going into the actual SmartEye Pro software, you can see the images from the 5 cameras, which are already calibrated. And as we apply the algorithm or click track, you can see how quickly and automated the profiling process is done and the tracking begins. During this case, I'd like to focus on the 3D world model, which you can see at the bottom, which is a unique function to the SmartEye Pro. You can see that this is an exact replica or representation of the actual environment from the picture that we viewed previously. This is the best visualization and probably the easiest way to get gaze intersection with the objects of interest identified in the requirements. So to go through the model, you can see the objects, which are labeled. We have cameras 1 through 5. We have the IR flashes, which again we'll discuss in the next case. And you can also see the point of origin here, which all objects in the world model and all of the data points are measured from. We use the world coordinate system to provide 3D XYZ measurements, which is very important in how we present our data. This really simplifies the data as the point of origin is always static, which really makes gaze mapping and post-processing and analysis a much easier task. You can see as gaze intersections occur, the objects are lit up and the object name is displayed in real time in the output data. You can also store multiple different 3D world models and easily change to fit another experiment or an application. So this leads us to our next case, which is going to be an instrument vehicle setup. This video shows the actual application which was used. You can see that the versatility of the system allows us to use the same system to work in a completely different environment. So on this one, we used 4 cameras instead of 5, which gives us 170 degrees field of view from side mirror to side mirror and through the windshield and the instrument cluster. And then this 4th camera down gives us good accurate tracking on the center stack as well. So you can see that we have a completely different world model to represent the cab of the truck here. So here are all of the features. So here are all the objects and how they're labeled for this experiment. Okay, there's a couple of features of the advanced system that Rob had pointed out that I'd like to mention here. One is our ability to work in all lighting conditions, as was demonstrated in the truck video, which was filmed outdoors. We create our own light using pulsating IR light through the IR illuminators. This system is completely insensitive to any ambient light and can maintain tracking through rapidly changing lighting conditions. The other is the size of the head box and the freedom of the movement with the subject. The robustness of the system allows for this as the subject moves and may either occlude or be out of view of one or more of the cameras. There are other cameras there to maintain the tracking. And this is very important for all kinds of experiments to allow this freedom of movement and naturalistic behavior while not only experiencing minimal loss of data, but also a very low risk of losing calibration. This leads me to my final area that Robert mentioned in the preceding slides that I'd like to discuss, which is data collection and accessibility. The system is highly rich in raw data as we provide 145 unique fields of data, which are timestamped and easy to sync. Just to touch on some of the more advanced data fields, you'll find very complete data with head position and rotation. We pump out 6 degrees of freedom with the head. Eyelid opening for drowsiness type studies. And finally, with pupillometry, which is really important for psychological or neuro studies, drowsiness, and used widely in cognitive workload studies. We make our data very accessible in the fact that we can stream it in real time through UDP or TCP. We can output it via CAN bus, or we can create a log file locally in CSV format, which is easily transferred to Excel or MATLAB. Another important thing to note is that you always have ownership of the data and always have complete access to the raw data. Additionally, we have an API, which allows you to remotely control the system from other computers. And finally, we have integrations already built with some analysis partners and also with several biosensing tools. With that, I'm going to turn it back over to Aaron Galbraith for a little bit of wrap up and to begin our live Q&A session. Thank you.
Thank you, Brent. During the presentation, we've had a few questions come in. Please use the Q&A section if you have questions, and we'll answer a few of them now. Okay, so we've had a couple of questions come in here. Let me take a look real quick. First question I have is, during the demos of the software, I noticed that no one was wearing glasses. How does the system work with people who need to wear glasses to see well?
Hi, Aaron. Yeah, I can go ahead and take that one. Yeah, so eyeglasses or eyewear can pose a challenge with pretty much any type of eye tracker. What we do is we continuously work to improve our algorithms and work with not only all different types of eyewear, but also any other occlusions on the face. But really, regardless of the frame size or shape or any special subscription or thickness of the lenses, may have you, in ideal conditions, we like to claim that we can work with around 85% of the subjects that come through and sit down in front of the system.
Okay, thanks. So I've got another question. It says, how do you calibrate the eye tracking system?
I can take that one, Aaron. So calibration of the system is very simple. Essentially, all you have to do is show the cameras a small chessboard pattern. The process takes about 5 seconds, and once you're done, the calibration is done and the system should be good to go, unless you maybe later on you bump a camera. If you bump one of the cameras, then you'd have to recalibrate. Again, it takes about 5 to 10 seconds, and you can test for hours with that.
Okay, thanks, Rob.
Mm-hmm.
So we've got another question. Says, what impact does camera exposure time have on some of the eye tracking measurement parameters, such as gaze detection or blink detection? And I will go ahead and answer that question. So the camera exposure time, we basically bring the light up and then bring the camera, take an individual picture, and then we do this 60 times a second. So the system by default is a 60 hertz system. We do sell other rates, but that's our default system. As far as how does it impact the gaze detection or blink detection, we have buffers in place, and we have sliding windows of time where we collect data. There are some mathematical calculations performed on that data, and then we output the concept of a gaze, saccade, fixation, or blinks. Okay, next here. So we have the 3D model is interesting. How do you create a 3D model?
I can answer that. So the 3D model is actually very easy to create. I think Brant showed a couple 3D models of an automotive interior, which tends to be something we do quite often. I would say the process takes about 20 to 30 minutes. Simply, it's taking one of the chessboards, and we have a laser tool connected to it, and you can shoot the different parts of the vehicle. For instance, the windshield, you'd shoot the 3 corners, and then the software will actually draw that plane in your 3D model in exact position. So I would say, again, it takes about 20 to 30 minutes to do the whole thing. We allow you to create a number of different shapes like circles, spheres, the planes, as well as cylinders. Once you create your model, you can save that model so you don't have to recreate it later.
Okay. So I have another one here. Says, can you speak more about SmartEye's capabilities regarding pairing with other physiological sensors? How are they different sampling rates? Excuse me. How are different sampling rates accounted for, and are only specific physio sensors compatible? I guess I'll take that as well. So we do pair with other physiological sensors. So we have a couple companies that we partner with that can take the SmartEye Pro data that we output and can map it. A few ways were shown through the video. So doing gaze overlay or using a remote scene camera, for instance. As far as different sampling rates go for the sensors, it depends on the analysis tool that's being used. They will take in the information, they will flatten the data together and then output it. And yeah, I would say only specific physio sensors are compatible. And again, that's going to be dependent upon which analysis tool is being used and what sensors they support. So we have another one here. It says, can the software track non-human or non-adult subjects, for instance, infants, primates, etc.?
Hey, Aaron, I can take that one as well. So, yeah, we've actually had some success in tracking with primates. However, this is something we're not actively pursuing, or it's in our roadmap or our offering. But with regards to children, the facial structure of a child or an infant is quite different from adults. And actually, we've recently just developed and released an infant tracking module, which accommodates for these differences. And this does allow us to track infants and children quite well.
Okay, thanks. So I have another one here. It says, I'm wondering what is considered as a good percentage for the gaze for a car environment as a rule of thumb.
I think that would probably be dependent on what your research objectives are. Typically, our customers want side mirror to side mirror coverage, which is about 170 degrees, and then they often want additional coverage down the center stack. The SmartEye system, we can get down to about a ½ degree of accuracy with a multi-camera system. Some of our clients will want that type of accuracy in specific regions, and in other areas, maybe off to the side, they don't want that accuracy, so we can use an estimated gaze, but it really depends on the customer and what their research objectives are.
Okay. One of the questions says, I'd like to know about the eye safety requirements for infrared illumination. Should I do some certifications of my final product when using smart eye devices? And do you also provide all the IR illuminators? So the answer to the second question is quite easy. Yes, we do provide all the IR illuminators. And the answer to the first question is we do certify there is a standard, I don't know the name of it off the top of my head, but we do certify to that standard. So I'm not sure that you would have to perform your own certifications, but I guess it would be based on how strict the requirements are. One second here. So I have a question. It says, how many IR LEDs were used in your demonstration? Is the IR pulse driver packaged with the camera sensor or a separate module? So it depends on which of the demos we were looking at. I believe in the control room, that was a 3 IR system, and in the vehicle, I think it was also a 3 IR system. The IR pulse driver does come with what we sell. That's called the Expanator. So the Expanator is a silver box that controls the synchronization pulse between the camera and the flash or the IR illuminators. So another question there is there any risk for eye damage with the eye trackers? I think that ties into the previous question I answered. So there is no risk. We test it and it is certified to be running constantly for days on end without any kind of damage to the eyes. So another one regarding the heat maps, are they made automatically via the output of the camera?
Yeah, I can take that. So the heat maps are actually based on the gaze intersections on certain objects that are identified within any kind of analysis tool. So a couple of the analysis tools that we do work with do have the heat maps available. So and they're configurable based on what you would deem a fixation, based on duration of the actual gaze intersection, and also maybe how large that object is, or that the outlier might be. So that's going to determine what the heat map is. So it's basically based on that, and it's just the best thing is that you as a customer have the ability to go in there and augment that and deem what you consider fixation to make those heat maps more relevant.
Okay. So I think we'll do one last question here. How many cameras do you need in a car for interior sensing? Well, I guess I'll take it. So the real answer, or the answer, depends on the size of the vehicle, where people are going to be looking, what are the objects of interest you're interested in, etc. I would say anywhere from a 2-camera to a 4-camera system would be fitting. Again, it's really based on the needs of the system. You know, what are the requirements? Where does the gaze need to be tracked? How precise does it need to be? How accurate does it need to be, etc. Okay. Thanks for the questions. Please stay tuned to our webpage, emails, and social media for information on upcoming webinars. And in the near future, we have a few more webinars planned. We'd love to see you there. Thanks once again for attending the first webinar of 2021, and we look forward to seeing you again.
Thanks, everyone.
Thank you.